Okay, let's get going. Looks like everyone's away working on the assignment. So, has everyone in the room here finished the assignment? Yeah. That's why you're here. Okay. At the risk of annoying the people who have finished the assignment, I thought I might give a couple of hints for the people that haven't, because all of the debugging I've had to look at during the week has been missing certain key elements. So if you're stuck, they might get you on the right track. Right, so there's a quiz out. It's due next Tuesday. It came out on Tuesday. Today I'm going to talk more about multi-dimensional selection, or handling selection of multiple attributes. And we'll get started on joins. And I just realised I haven't got my slides and signatures in place, so maybe I'll have to talk about them next week. Right, here's another famous DB nerd. Clearly doesn't get paid enough to have a private jet, but he's got a small aircraft. Who is he? He's the guy who invented R-trees, which we'll be talking about later today. So he did that while he was doing his PhD at Berkeley, but then he didn't follow through with an academic career particularly. So he went and worked with Michael Stonebraker at Illustra, which was, I guess, in some sense a precursor for Postgres, and worked for a few other companies like Sun, and then Sun was taken over by Oracle, and he retired earlier this year. So interesting contribution. I'm not even sure that he got any awards for R-trees. You know, a lot of people, you come up with linear hashing, eventually you get an award for it. But I didn't notice any awards floating around. So he didn't publish very much either, just a few papers following on from R-trees. All right. So, we've been talking about hash selection on a single attribute. So, if you only ever care about queries on the ID attribute, then you can turn the file into a hash table, and all the queries on ID attributes work beautifully, i.e. they only go to one bucket. However, this is very hit and miss. If you don't ask a query that involves the hash attribute, then you get nothing. So you just got to do a linear search, and as far as the file is concerned, once you start using hashing, the order of tuples looks a little bit random. So you either get really good performance if you happen to ask a query that involves the hash key. If you don't, you've got a linear scan. Alright, so we can try and compromise a little bit and get okay performance on all types of queries. And here we're talking about partial match retrieval queries. So basically anything that involves a conjunction of equality tests on the various attributes. It may involve all attributes, it may involve one attribute, it might involve some of them. So, the way multi-attribute hashing works is it forms a hash value that's worked out from the hash values for the individual attributes. So it merges them together, and we'll see how it does that in a moment. So, for a typical query, you know values for some attributes, but you don't know the values for other attributes. So if I ask, A equals C1, then I know the value that I'm interested in for attribute A1. And maybe there's another attribute, AN, and I know the value for that. But there may be attributes 2, 3, 4 in between whose values I haven't specified. So clearly, I'm going to get potentially get multiple tuples based on that, as long as one of the query attributes is in the key. So, if we know some of the hash, then we don't have to look at all the pages in the file. So we can use, for standard hashing, once you've got the hash value, that gives you a page or a bucket and you go and look there, and that's it. With multi-attribute hashing, we can reduce the number of pages that are required to be examined, but we can't, I was going to say eliminate, but often we're going to have to examine more than one page to solve the query. And this strategy, it doesn't matter what kind of dynamic hashing scheme you've got, linear hashing, extendable hashing, whatever, this approach will work there, because essentially we're generating a single hash value each time, or we're generating a number of possible hash values in fact. Okay, so we got a file, and let's assume for the sake of argument it makes the discussion simpler that its size is a power of 2, so our hash value involves d bits. It's got n attributes. Each attribute has a hash function. They don't have to be separate hash functions. But if you want to generalize things, you can have a different hash function for each attribute. And each attribute contributes to the combined hash value some number of bits. So if we're asking, so you can see, if we're asking a query on a particular attribute, we're going to get a hash value for that attribute. The other attributes, we don't know what values we're expecting, so we have to put in some kind of unknown into the hash value. And then we have to resolve the unknowns to a whole bunch of specific values to look at the appropriate pages. The other thing, of course, is if we're hashing on d bits, then the number of bits that are being contributed by the attributes better add up to d, otherwise we won't be using part of our file. And we need some way to say, all right, for a particular attribute, the ith value in that attribute is going to contribute to the jth bit in the merged hash function. So a way of taking the individual bits from the attribute hashes and assigning them to the combined hash value. Alright, so here's an example database, typical example. So we've got 4 attributes, we got a very small data file at this point, and we only need 3 bits to hash the entire file, okay, 8 pages, 3 bits. And we take 1 bit from the first attribute, 1 bit from the second attribute, 1 bit from the third attribute, and use that to form the hash value. Of course, since we've only got 3 bits and we've got 4 attributes, we have to decide which attribute isn't going to be involved in the hashing, and we'll talk about how you might make that decision later on. So if someone does ask a query like this that involves the attribute that we don't have any hash information on, bad luck. It's just like the old scenario, if you've got a single attribute hash and you ask a query on a different attribute. So how do we decide how many bits to give to each attribute? We have to look at the kind of queries that are going to be asked, and we'll have a look in a bit more detail about how we use that information later. So here's a little bit more specific. So a choice vector is going to tell us, and it can simply be an array of pairs where one part of the pair says which attribute we're talking about, the other part of the pair says which bit from that attribute we're interested in, and this index value here tells us which bit in the composite hash value actually gets set. So the fact that we've got this pair here says from attribute 1 we're going to take bit number 0 and we're going to stick it in bit 0 for the combined hash. Bit 1 for the combined hash comes from attribute 2, and it's going to be bit 0 from attribute 2. And when I say bit 0, basically what I mean is the least significant bit in the hash value. Bit 2 comes from there, and at the moment we've only got 3, but we only need 3 bits for hashing because it's a very small file. But in theory, you know, as the file expands, if we're using linear hashing, for example, then we'd need to consider more bits. So basically what the choice vector says, for each bit in the combined hash value, this is the attribute it comes from, and this is whereabouts in the hash value for that attribute we get it. Right, so if we've got a tuple like this, we can form a hash value for that tuple, which of course tells us whereabouts in the file to locate that tuple by taking the least significant bit from the first attribute, least significant bit from the second attribute, least significant bit from the third attribute, and sticking them all together to get a hash. Okay, so I'm deciding where these arrows go based on the information that I had over here. So that's fine. So we can form a hash value and we can locate the tuple somewhere in one of the pages of the file. Alright, so let's assume that the maximum hash size is 32, reasonable maximum. Hash values are just 32-bit strings, and we imagine that we've got a function that will extract the ith bit from a hash value. That's how you can implement that. It's reasonably straightforward. And the choice vector consists, as I said before, of an array of pairs where each pair tells us which attribute and which bit from that attribute we need to deal with. A choice vector itself is going to be an array of those pairs. Right? So this is a relatively small data structure too, so it's not like we're creating something gigantic. And then we've got hash functions. Potentially we can have a separate hash function for each attribute, or you can simply use some kind of generic hash function. Right, so how do we produce this d-bit value given a tuple? And of course, when we're inserting a tuple, we obviously have all the values for all of the attributes. I guess you can argue that null is a specific kind of value that we can hash potentially. So we're given a tuple, we're given a choice vector, and we're given a number of bits that need to be set. So first thing we need to do, we assume that somehow we've generated a bunch of hash values, one for each attribute. The result hash value that we're going to get is just stored in a hash value variable, and we're going to have another 32-bit quantity that's just going to hold a single bit that we can use later on. Alright, so we iterate across all of the attributes. We actually use that hash function to produce the table of hash values. Right, we then iterate through as many bits as we need, so 0 up to d bits, or d minus 1 bits, and for each bit in the combined hash value, we work out which attribute it comes from, we work out which particular bit we're interested in, we extract that bit from the hash value, and then we OR it, bitwise OR it into the overall result at the appropriate location. Yeah, alright, so I is telling us which bit of the final hash value that we're talking about. And once we've produced the hash value d bits, that's the combined hash value that we return for the tuple. Alright, so let's take a look at an example. So we've got 6 bits that we have to produce. 3 of them come from the first attribute, 2 come from the second attribute, and 1 bit comes from the third attribute. And we can kind of work that out by looking how the bits are produced from the choice vector. So we can see that attribute 1 produces a bit here, it produces another bit here, and it produces another bit here. Attribute 2 produces that bit and that bit, and attribute 3 just produces that bit. And we're only interested in the first 6 of these. Now, right, so these are the hash values that we're dealing with. So I think I've got let's try that one. Good. Okay, so here's our choice vector up here. Here's our hash values for the particular attribute values that we've got. So what we want to do, produce the various bits of the hash values. So the first thing, the choice vector tells us from this particular hash value, we take that bit, and that becomes the least significant bit in the combined hash value. For the second attribute, we use the same hash value, but we take the next bit, stick it in the combined result. For the next bit in the combined result, we take the least significant bit from the second attribute, which picks up that one bit, and so on and so on, and eventually we end up with a composite hash value like that. Okay, all very nice. At this point, we're building hash values. But what about when it comes to querying? What do we do? Well, if we're lucky, we know the values for all of the attributes, and we're effectively just asking, does this tuple exist in the table? But in general, we don't know the values for all of the attributes. That's why we're asking a query. We're trying to get tuples that satisfy these conditions. Okay, so here we're trying to get all of the accounts at the Brighton branch that are owned by someone called Green. Okay? We're not going to keep writing out select queries because they're too long. We're just going to write them out like this. So basically, this is asking the query. The branch name is Brighton. I don't know what the account number is. I do know that the owner of the account is called Green, and I don't know the amount. So presumably what we're trying to find out is what are the accounts and how much is in each account. Or in fact, what we're trying to find out is just the amount. So this, we're going to start using this notation in all the rest of the slides about multi-attribute hashing. So we know the hash value for Brighton, we know the hash value for Green, and using those two bits and the choice vector, we can set some bits in the combined hash value. However, we don't know the value for this attribute, so what do we put? We put unknown value. Okay. So what have we learned from this? We haven't got a specific hash value giving us a specific page, but we've got some information. So any tuples that have Brighton and Green are going to be in pages that have those two bits set to 1 based on whatever the hash value is here. Maybe it's got a 0 in the low order bit, or maybe it's got a 1 in the low order bit. There are two possible values that we could have for this bit, this unknown bit. So we could either, so all we need to do now is look in pages 101 and 111, and if there's any Brighton Green tuples in the table, they're going to be located in one of those two pages, and maybe we have Brighton Green tuples in both of those pages. So we haven't restricted ourselves to looking at just a single page like we do with regular hashing. That'd be nice, but at least we've only got 2 pages to look at rather than looking at more. All right, here's a worst case scenario where we only know the value Green. So we can get a known bit for the hash value from Green, but we've only got unknown bits in all the other hash values, so now we've got 2 unknown bits. Okay, so if we want to find tuples in the database, well, if they had Green in them, they're definitely going to have a 1 in this position, but could be either 0, 0, 0, 1, 1, 0, or 1, 1 for those unknown bits. So now we need to check 4 pages, and you can see, well, we've got to check half of the file, given that we got an 8-page file. So that's not great, but at least we've got some benefit from the hashing still. So let's have a look at how we might form hash values. So we've got, here's a different database, 6 bits, that's the choice vector 1, 2, 3, 4, 5, 6. So we've just given you enough of the choice vector to form those 6 bits. So what are the query hashes for each of those queries? And I think I've got too many files with similar kind of names. Is that the one? Yes, it is. Cool. I think it is. Alright, so the first query, we're basically asking, we know all of the information that we're interested in, we're really just asking, is there such a tuple in the table? And so we can form a completely specified hash value because we know the values for all of the individual attributes. So, well, let me see. So the 1, 0 from attribute 0 goes there. So here I've numbered the attributes differently to what I did before, but there you go. The next bit comes from the low order bit of attribute 1, the second attribute. So that's where that bit comes from, and you can work your way through the choice vector to work them out. Alright, if we've got the bit, the attribute in the middle is unknown, so here we're asking a query, select from this table where the first attribute is A and the last attribute is C. And we don't know what the middle attribute is, so hopefully we're going to find a set of tuples that satisfy that. Well, given that we don't know attribute number 1 in this case, we can't set that bit and we can't set that bit, so that's producing those 2 stars there. So the pages that we'll need to look at in order to work out whether there are any such tuples that satisfy that are ones where the 2 stars are replaced by 0, 0, which is what we got there, or 0, 1, or 1, 0, or 1, 1. Okay, so that's how we've generated all of these page numbers. And if you want to put it another way, how we've generated 4 specific hashes from a less specific hash value. If we don't know the first attribute, then there are 3 unknown bits. And of course that means we're going to have to look at 8 pages. So we got, what are the possible values for those 3 unknown bits? 0, 0, 0, 0, 0, 1, 0, 1, 0, blah, 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 up to 1, 1, 1. So I didn't write all of the values, but this first one here is produced from 0, 0, 0, okay, by filling in all those stars with 0. Second one's produced from 0, 0, 1, and so on. Alright, if we don't know the values of the second and third attributes, then they're the bits that are unknown, and once again 3 unknown bits. To find matching tuples means we have to look at 8 pages. And of course, if the query doesn't specify anything, then we've got to look at the whole file anyway, so that doesn't help. At least we've got these 6 unknown bits, so we can just set them to all of the possible values between 0 and 63, which is essentially scanning through all the pages. Alright. So how do we answer queries like this? And you should have a clue from what I've been saying in the previous few slides, but how many unknown bits there are, and this this is splitting the algorithm in half, so we don't have a super long slide. So we look at each attribute in the query. If the ith attribute has a value in the query, so in other words, if we said if attribute A1 equals 5, so that's what effectively what that means. If it doesn't have a value, it's not. If we're talking about a select query, it's not mentioned in the where clause, and if we're talking about that notation I've been using, basically it's a question mark. So, if this particular attribute I has a value, then we use the hash value for that attribute to set the appropriate bits in the overall hash, and we can do that using the choice vector. So here we're not doing it a bit at a time like I've been doing before. For a particular attribute, we just take all the relevant bits and stick them into the appropriate places in the combined hash. If the attribute doesn't have a value, then once again we use the choice vector, but rather than putting in zeros and ones that we derive from the hash value, we simply put in stars because we don't know what those bits should be. And we increment the counter for the number of unknown bits. Okay, so at this point, we've set up a partial hash value that we can use to work out which pages of the table that we need to read. So we open the file for reading, and then what do? We need to iterate for each of the possible values for the n stars unknown bits. So that's, or if we've got d unknown bits, there's going to be 2 to the d possible values for that. So that's an attempt to render in C 2 to the power n star. So I guess I could have used a left shift to do that as well. So that's the number of times we have to go through. We've got our composite hash, which has got known bits and unknown bits, and basically we use the current value of I and the choice vector to generate a specific hash value, which gives us a specific page P, which we then read into a buffer. And of course, we still have to, as we've done in most of our indexing schemes and so on, and our hashing, we've still got to read the page, because all that the hash is doing for us is pointing us at a page, and then we've got to run through that page and check whether each tuple satisfies the query, and then we can add it to the results if it does. So that's going to, this loop is going to iterate 2 to the n stars times and generate a specific hash value each time. Alright, that's an interesting question. So I've been talking about bit strings, and some of the values in the bit string are 0, some of the values in the bit string are 1, so that's nice, that's binary. And then we chuck in this extra value, star. So how can we possibly represent that as a bit string?
I think you'd have to use a second bit string and maybe have like 1 means star and 0 means not star.
Spot on. Ooh. Where's that gone? Oh. Yeah. Another possibility is to use a character string, so we can use 0 for 0, 1 for 1, and we can actually use star. So that would be one way to do it, but the way you were suggesting was like this. So 2 bit strings, one giving us the real hash bits and one giving us the unknown bits. So we know that, and I guess we should never see a 1 here if we've got a 1 here, because we wouldn't know what value to put there. So we wouldn't have ever put a value there. So you can, hopefully, I've got this right. Yeah. All the 1 bits in the unknown bits array never have a corresponding 1 bit in the real hash bits. So it's pretty easy to represent. So in this case, 2 32-bit words. So we're still not looking at massive space overhead to handle this stuff. see. Yeah, alright, so here we're not going to bother forming values because we know all we're interested in is how many pages do we actually have to look at. Right, so this first query here, we know all the bits. That's going to give us a hash value that's completely specified up front. So we go straight to that bucket and we're done. If we've got a query like this, then we know the bits for X, we know the bits for Y, we don't know the bits for Z, but there's only one bit for Z, and therefore we only need to look at 2 pages. The possible values 0 and 1 for the bit that we don't know. If we ask this query, then we know the bits for Y, but we don't know the bits for X and Z. And there's a total of 6 of them, so we need to look at 2 to the 6 pages, which is 64 pages. If we know the value of Z, that only gives us 1 bit, and there's 8 bits that we don't know, so that's 2 to the 8 pages that we need to read. So that's potentially slightly annoying to us. So how big is, in fact, we need to look at half the file basically.
And that's ignoring overflow pages, I guess.
And including overflow pages, yeah. The file structure is exactly the same as we had for hashing before. And if we have a query like this, we're stuffed. So we can't use hashing at all for that. So we just have to examine the entire file. Alright, so what's it going to cost? Oh, we've just pretty much looked at that, in fact. So the number of different possible query types, number of combinations of known and unknown attributes. For n attributes is 2 to the n. There's a different cost for each different query type, basically determined by the number of unknown bits. And this is where things start to get slightly interesting, that certain queries are more likely, certain types of queries are more likely to be asked than other types of queries. And if we happen to know that kind of information, and often it's almost workable outable, because databases are often accessed from web applications, and there'll be queries embedded in the web application, and we can see what kind of queries are actually going to be asked. One thing we don't know, given that, is the likelihood that particular query is going to be asked, unless there's some way we can work out the control flow through the web app. So, we can talk about a query distribution which gives the probability that each particular type of query might be asked. What do we know here? I think we've covered that pretty much. In fact, I should have removed that slide. Alright, so keeping on with the cost. So obviously the best case scenario is we're given values for all of the attributes and we go to a single page and we're done. The worst case is we don't know anything, or we get a range query, something like that, and we got to scan the whole file. What's the average cost going to be? Well, for a given query type, the cost is determined by the attributes that don't appear in the query, and so each of those attributes contributes DI bits, and therefore the number of pages that we need to read is just the product of all of those unknown bits. If we ignore overflow pages, but overflows exist so you can easily add them into the equation like we did down here, then that's the number of pages that we need to read for a particular query type Q. Right, so the minimum cost is 1, like I said before. Maximum cost is read everything, and the average cost is determined by that. Now there's a interesting interplay between those two values there. If you happen to know that a query is likely to be asked, and you know what attributes are involved in that query obviously, then you might want to allocate more bits to the attributes in the likely to be asked query. So that's just a weighted sum of all the query costs based on the likelihood of being asked. So for a given application, it might be handy if we try to select the choice vector, or select how many bits we want to allocate to each attribute based on the kind of queries that are going to be asked. Now, how do we decide how many bits to allocate to an attribute, or how many bits in the composite hash value to allocate to an attribute? Well, one thing, as I said before, if we've got a query that's extremely likely to be asked and we know what attributes are said in that, then those attributes probably should get more bits. Of course, if we've got an attribute that has 2 possible values, or 4 possible values, like, what's an example? Gender these days would probably have 4 possible values, male, female, I'm not going to tell you, and something in between. Okay, so 2 bits, so there's no point allocating more than 2 bits to an attribute like that. And also, once again, selectivity kind of notions. If an attribute is highly discriminatory, it'd be worth allocating more bits. So this turns into an optimization problem, and you can use standard optimization techniques. So as long as you know the query distribution, you can work out the D values that give you the minimum average cost. So here's an example. So we've got a table, the table that we had before, 4 attributes, which I've abbreviated to these things down in the table. So here are all of the 16 possible query types, given that we got 4 attributes. We know that's the case. So unknown attribute, then we've got to look at, and here we're assuming, what did I say? I didn't say anything. I'm assuming D equals 3, and we're getting combined hash bits for the combined hash from BR, count, and the name. So the first 3 attributes are contributing to the combined hash value. So let's say that frequently, or relatively frequently, we ask a query that just says, what accounts have you got at a particular branch. So that happens a fair bit of the time. We know that it's going to cost us 4 pages. All of these ones are 0, who are basically queries that never get asked. If we happen to know an account number and a name, and we want to find out which branch it's held at and how much money is in it, then that query is going to cost us 2-page lookups, because there's only 1 unknown bit, and it happens relatively frequently. The most frequent query, however, is to work out the account number. A bit of a strange query, but given a person's name, given a branch, given an amount in the account, is there an account that satisfies that condition? So in that case, once again, there's 1 unknown bit, so there's only 2 pages to look up there, and that is a relatively frequent thing. Here I kind of preempted things by giving the same number of bits to each attribute, but if I had more bits to play with, then I might want to decide that to allocate fewer bits to this particular attribute because it's unknown in a query that's frequently asked. But if I allocate less bits to it, that query is going to be answered more efficiently. So here's a bit of consideration of that. So imagine now that we haven't got just 3 bits, we've actually got 14 bits because we've got a decent sized table, and if you're talking about a bank database, you probably do have a decent sized table. So the attribute branch occurs in the two most frequently used queries, or the most frequently asked queries. Therefore, it'd be useful to allocate a lot of bits to it. The attribute name also occurs in frequently asked queries, so it'll be worth allocating more attributes to it. I can't remember why I decided to allocate less than probably because the branch attribute is more discriminating. So, and we're kind of assuming that we've got at least 2 to the 6 different branches. So if we know the branch, that's going to target just one particular branch, and so we give more bits to that. Name isn't going to be particularly discriminating, I don't think. All right, the amount, we need to allocate a couple of bits to that because it's used in the most frequently asked query. So 2 bits would do. Once again, amount's not particularly discriminating. You have a lot of accounts with $500, a lot of accounts with $1,000, although if you want to argue, there's not going to be many accounts with a specific amount in it, so you could argue that it's more selective. And the account attribute occurs in the quarter of the query, so we can give some bits to that as well. So if you wanted to sit down and do the optimization by hand, then you could. And I think maybe I did, and I discovered they were the optimal values for those choice vector, the number of bits for each of the attributes. But you can get a rough estimate just by considerations like that. Oh yeah, if you want to know what the cost is for this, remember there are only 3 queries that actually get asked, so they contribute to the cost. If it doesn't get asked, it doesn't cost anything. And so that's the average cost. So, and basically what that is, number of pages you've got to look at. Obviously it's not as good as 1, but given that we've got 10,000 pages, not bad. The average cost is that. This query, the most frequently asked query, gets answered particularly efficiently, so that's good. Of course, these ones aren't quite so good. Obviously, each of these is 256 pages that we have to look at. Where are we? Right, so here's another example. So we can think about how we might want to come up with a choice vector for this example. So we've got name, gender, and age. And these are the likelihood of asking particular queries. Seems a bit strange that we'd ask that query so many times, but there you go. Who knows? That's what happens. How do you work out the likelihood of asking a query? Well, possibly you know something about the application that will tell you that. Another way to work it out is just to observe the queries on the database and see what kind of queries are asked and how frequently they're asked. Alright, so now let's quickly have a look at this. Alright, so this is the same table, 32 pages, therefore 5 bits of hashing is needed to deal with them, which I've said down here. That's the likelihood of asking the queries. How many bits to allocate to each attribute? Well, name domain, very large, and it's used a bit, so we don't want to allocate too many bits to it, because we're not going to, given a name, it's not going to help us that much. Gender, there's only 4 possible values, like I said before, so 2 bits. It's used in a lot of queries, so we want to allocate as many bits as we possibly can to that attribute, but there's no point allocating more than 2 bits because you're not going to learn anything new if you do. And the age, the domain, I've been very generous here in assuming people live for a long time. I could have made it 128, that might have been more plausible. I'm sure someone will come along with a 130-year-old and ruin my assumption. It's used half the time, so allocate a few bits to it. So that's for the example, we've only got 5 bits to play with. If we got 20 bits to play with, we'd probably want to allocate more bits to the name and more bits to the age. And there's no point ever allocating more than 2 bits to the gender. So you can use heuristics like that to come up with a rough allocation of bits to attributes. This doesn't give you a choice factor, you've got to make decisions. Where do those 12 bits end up in the combined hash? That gives you the choice factor, but at least knowing how many bits are useful is a good start. Perfect. All right, let's have a break at this point and we'll start again in 10 minutes.